So what I want to talk about today is something sort of in the broader theme, the sort of landscape around this workshop, which is thinking about some of the phenomena that go on inside giant social networks, and what we've been learning from being able to observe them in the online domain. And this is going to be joint work, actually, with two people, a former PhD student of mine named Lars Backstrom, who's now the director of the newsfeed ranking group at Facebook, where he essentially manages the group that develops the algorithm that decides what goes in people's newsfeed. And my current PhD student, Johan Ugander, who is graduating this year. And the idea sort of is that we've been thinking about, all of us have intuitions about our own social environments. But somehow social life had always been this thing that was sort of fleeting and ephemeral, very, very hard to measure. And that changed abruptly once people began carrying out a lot of interaction online, right? People began messaging each other, posting content, commenting on each other's content, searching for information, sharing information. And all of these things became visible to algorithms and to computation. And so we began to look at things we couldn't see before, right? So in the same way that somehow science always advances when you take things that were once invisible and make them visible, right? And that happens with deep space imaging, and it happens with looking at cells. And it's sort of, in a way, happening now with a lot of these social processes, that we have data on them, on things that we've always sort of lived with and had intuitions for, that we just didn't have before. And so, in a way, it's sort of a mapping activity. And one's reminded of lines like Jim Gray's line from about 15 years ago when he won the Turing Award in computer science, that he thought of the emergence of cyberspace and the World Wide Web, which was about maybe 5 to 7 years old at that point, as being like the discovery of a new continent, right? The sense that we've really found something new here. And at the time, I had just started my faculty position at Cornell a couple of years earlier. That's how made a big impression on me, and sort of all the language around that we are supposed to go out and map and try to figure out what's there. Right? And the question becomes, how is this mapping activity different from other mapping activities? And I'll talk a bit about this. But sort of one thing is this kind of duality between the sort of two different ways of looking at the online world, right? One is the idea that the online world is a phenomenon to be studied, right? So for people who think about building computer systems, right? You build a system and you run it. They tend to be surprised when the online world reacts in ways that they didn't expect, right? Because the design principles of social systems don't just include things that computer science as a field was traditionally comfortable with, like scalability and efficiency and things like this, but it also included these sort of social feedback effects, right? The way in which audiences react to things, the way in which groups of people react, the way in which incentives operate, and all of those kind of rebounded on designers in unexpected ways, right? So it had this kind of organic nature to it. It needed to be studied on its own terms. On the other hand, there's a flip side to that, which is that if you go too far in the organic direction, you think about it as, okay, the online world is this organic thing, we're just going to watch it evolve, then you're going to be surprised in the other direction, right? That if you watch Facebook and you watch it evolving, but then you sort of step around to the back side, you discover that there are all these knobs and dials that are being turned, right? And my colleague Lars, who I mentioned on the first slide, is certainly one of the people who is most turning all of those knobs and dials. And the question is, what is it that you're actually seeing online is being algorithmically managed? Because after all, your friends collectively on Facebook, if you're an active Facebook user, produce maybe 1,000 to 2,000 pieces of content per day. Right? So that's 10 times the size of a very active inbox in your email. You're not going to be able to consume all of that. And so there's some filtering. There's some choices. Do I show you things from close friends, from distant friends? Do I show you more photos, more text? Right? These are all choices. And there's no default choice here. You have to choose. And so there is a kind of design aspect to this also. And so that's what seems kind of intriguing. We're trying to map this world. It has its own principles. It behaves in sort of ways that are predictable and organic. But on the other hand, it is partly being designed by us. OK. And so what is the terrain of this world? It's many things, right? It clearly has a big dose of geography. It incorporates all the social structures that we bring from offline life. And it also is graph theoretic. And in some sense, in the sort of competition for mind share here, graphs, I would say, have been doing quite well, right? So if I think about, by graphs, I mean simply, thinking about objects that are connected, right? And so I've drawn here two different graphs. Each of them has lots and lots of components, so it's hard to see, but right, lots of points connected to the other things. So on the left, just as sort of a guide to this, I've drawn this beautiful picture that Lada Adamich and Natalie Glantz drew of the blogosphere before the 2004 US presidential election. And you see all these left bloggers on the left and these conservative bloggers on the right. They're linking to each other a lot. They're linking less, across to the other side, right? So it's a graph. It encodes relationships among things. And we see something immediately, right? Polarization jumps out at us. And on the right was the trace of an anti-war chain letter petition that David Libanel and I studied starting in 2003. We studied actually over a course of 5 years before writing a paper about it. And again, we see that there are a bunch of individual nodes here, and each node passes the chain letter on to some other nodes, and they get linked together. Right? And we get a very different looking kind of graph, right? One that sort of spreads out like a tree spreading information. And I think what's sort of striking about the way in which graphs have sort of entered the language of this topic is that in a way where once these dot and line pictures were sort of esoteric and mysterious, now they're really sort of ubiquitous. So the polarization really begins to seem to us as a big graph with a bunch of nodes connected to each other where there are these two clusters that are not talking. And political mobilization, right? Getting the word out, spreading information, that begins to look like this big branching tree-like structure as it spreads out. Okay. So graphs are certainly going to be part of the language here.
Are those real data?
Yeah, so these were the actual bloggers. So here, basically, you just went in, what Lotta and Natalie did was they downloaded a whole bunch of blogs. They found what the links were in them, and they did a spring embedding of this graph. This we actually, so the nice thing with a chain letter petition is that you go and you search on Google for the header of the petition. You get 1,000 copies or so. And then everyone has signed it. And so I have these big long lists of names, and this long list of names is a subset of that long list of names, and so I can paste them all together.
The size of circles, the number of bloggers in the blog?
Yeah, so the popularity of the blog is, yeah. So some circles are slightly bigger than others. But keep in mind, the circles are very small, and that's a whole bunch of circles there, yeah. OK. And these are just sort of the kinds of pictures that once, and we'll stare at others of these pictures, right? So I'll be talking about some data from Facebook, and neither this nor this came from Facebook, but they're the kinds of pictures that we draw, right? And so it's sort of good to get comfortable with, so this is what polarization looks like. This is what spreading the word to lots of people maybe looks like. OK. So as a mapping activity, though, the other interesting thing here is that there's sort of the shock of the familiar, right? So we're taking algorithms and massive data sets, and we're aiming them at things that we sort of feel like we understand intuitively. We sort of understand political polarization, or we have an intuition about it. We have an intuition about mobilization. And so this notion of what does our everyday life look like when viewed by algorithms is sort of an interesting thought experiment, right? Because the algorithm shows up, and it has unbelievable power to detect patterns at very large scales that we don't have. But it lacks any of our domain knowledge, right? So all the kind of knowledge of the world that we bring, the algorithm does not, right? It only sees what's there in the data. And so when I think about that interesting dichotomy, right, these super powerful beings watching our lives, right, able to detect patterns but knowing nothing, I'm sort of reminded actually of a lecture I went to 20 years ago now by Carl Sagan toward the end of his life, 1993 on the Cornell campus. Carl Sagan was, of course, a much beloved figure at Cornell, and although Carl Sagan's sightings were rare since he traveled a lot. But he gave a talk on the Cornell campus in 1993 that was entitled, "Is There Life on Earth?" Kind of a strange title. It was actually a talk about a paper he had published in Nature that year. Nature had put that question on its cover, "Is there life on Earth?" The title of the paper was actually slightly longer, "A Search for Life on Earth from the Galileo Spacecraft." And he asked a question which, metaphorically speaking, is the question I ultimately found myself coming back to 15 or so years later. What had happened was that, so the Galileo space probe had taken off from Earth to do one of these exobiology things where it goes out and looks for signs of life on the moons of Jupiter and Saturn. And to get to the outer solar system, it had to actually like slingshot through the inner solar system and then head outward. That's kind of one of those things they do. And so it kind of wrapped around Mercury or Venus and then started heading back out. And as it did that, it actually passed by the Earth again on its way back out. And it had this whole battery of instruments, and it aimed them down at the Earth and collected a lot of readings. And Carl Sagan's point was that, if we're going to go and look for subtle signals of life on the moons of Jupiter and Saturn, at the very least, as a kind of control, we should be able to detect evidence of life on Earth. Because if we can't do that, then this whole thing is probably a bad idea. And so his lecture sort of asked us, do the following thought experiment. Pretend that we are all in the audience Martian scientists looking at these signals coming off the Earth. What would we be able to infer about the Earth, and would something stand out for us? And he talked a lot about a whole bunch of physical and chemical signals. And actually, as I recall, the big thing that would jump out to Martians, he claimed, was the oxygen-methane coexistence, that much methane should not be there without combusting unless something was replenishing it. And then he sort of derived a bunch of stuff from that. The point being, you look and you say, what would someone just from the data be able to do? Now, I find myself now sort of thinking back a lot about Martian scientists. But in this case, the Martian scientists are algorithms looking at a lot of data about us. And you ask similar questions. What could they tell, knowing nothing but being kind of very, very powerful? And there was actually a life on Earth experiment that I did with Lars and also with Dan Huttenlocker and Dave Crandall, which I actually talked about the last time I was here at IPAM a couple of years ago, right when we were starting to think about the Facebook data. And the idea there, just to sort of mention in a couple of slides, was we took all the photos that were being uploaded to a big social media site. Right? So every time you take a photo, you put it on a map. You say, this is where I took the photo. And so you imagine sort of there's a big black canvas like that. And then we're going to put a white dot everywhere at the latitude and longitude of every photo that got uploaded. Right? And when you do that, you ask yourself, what kind of shapes begin to appear? What do you see? Do we see some kind of pattern when we take 100 million photos all being uploaded with lat-long designations? And shapes do appear, and they kind of look like that. Right? And I want to mention this because we're going to start looking at things that are going to be a little murkier, like graphs. And we want to sort of develop some intuitions about what is it that we're seeing here that we might try to then see later on, right? So obviously one thing we're seeing here is, bright spots. So the density of points, right? We look at where the density is. Obviously this photo sharing site is not being used equally all over the world. It's big in Europe. I only showed the Eastern Hemisphere here. It's also big in North America. But things go up to the edge of the water and then don't go any further. There are particular bright spots, Paris and Madrid and Rome and a bunch of other things. I showed this picture in Riga, so I had to work hard to figure out where Riga was, and it was one of these. And then there are places, but there are a couple other things that we have to think about, right? So one is we should look for coastlines. But sometimes the coastlines mean that people can't live there. Like here, you can't live there. And some is just that people don't live there, like in the Sahara Desert. And some is that people do, but they're just not on the site, which for our purpose is the same, right? A lot of people here, a lot of people there, they're just not using the site. We see other things, right? These bright spots where the density is. We also see sort of these one-dimensional threads, right? So this one-dimensional thread, which is actually the Nile River. This one-dimensional thread here where affluent Westerners bring their digital cameras and climb tall mountains and take photos of them. And a whole bunch of things, right? So we should remember that, right? Look for where the density is. Look for where these boundaries are. When you see a boundary, ask, is it because people can't live there or they just don't live there? And also these one-dimensional threads that go through the data. OK, but what we'd like to do is try to do this activity, this mapping activity for graphs, for the networks that we see. And so I'll talk a little bit about the mapping that we did. And then I'll actually try to zoom in and ask about a concrete question that we looked at in the Facebook context, where we tried to really get into something about these graphs. OK, so the Facebook graph, right? A billion-node network, and a billion's number of active users, right? People who are actually using it on a monthly basis. How do we discover the structure of this, right? The sort of strange geography of our collective social experience. Something we all have intuition for, but have never really looked at in the same sort of way that we look at a map. So obviously we could take the nodes and we could put them on a map. That's sort of a cop-out, right? It creates this beautiful visualization that an employee of Facebook produced in late 2009. But that's not the point. We want to look at the intrinsic structure just formed by the connections. And the problem is that a billion-node network is, in every real sense, sort of incomprehensible to human beings. I think that's sort of part of the point. It's large. It's amorphous. It's very dense everywhere. And so I'm not going to try talking about what the whole billion nodes look like. I'm going to instead do something that you sometimes do when you have a very complicated mathematical object like this billion-node graph, and you want to understand it, which is you look locally. You say, let's take every point in the object, and let's look in the vicinity of that point. Right? We'll kind of localize around each point. We'll talk about what it looks like locally, and then try to understand something from that. Okay? And so the idea is, let's look locally around individual points. Here's the next graph I wanted to talk about. This was also produced at Facebook in 2009 by Cameron Marlowe, Lee Byron, Tom Lento, and Itamar Rosen. This was, what was this? This is a Facebook employee and all of his friends. Okay? So basically, at the center here is an employee of Facebook who decided to sort of donate his network to science so it could be studied. And these are all his friends. And we produced, so when they drew this picture, drew a link between every pair of his friends who were friends. Right? So a link here means these two friends of his were friends. And then they used a spring embedding algorithm to lay it out nicely so that big clusters of links would all kind of group together, and ones that were not so connected could stay apart. And they imposed a constraint that had to kind of radially fill out the space, which prevented it all from just contracting to a point. And so you get this picture. And there's actually a lot going on here, right? So we can actually do a run through our playbook here of like, let's look for regions of density, let's look for boundaries. And we see, for example, there are obvious clusters in this guy's life, right? These people all know each other. Those people all know each other. These two groups don't really interact very much. And that does say something, right? In fact, these are his coworkers, right? So these are clearly two different parts of his life. And then there are other smaller parts of his life, right? Some clusters here and here and here. And in fact, these are his coworkers at Facebook. These are actually, he was a Cornell alum. These are his friends from college. There's really not much overlap there. Somewhere in here is his extended family, because on Facebook, your extended family, unless you're a very unusual person, is not this big or that big. And so it's one of these things. And so you can actually, and you can spend some time looking at these, and you'll get a bunch of them. Actually, one thing that's striking is how similar they all look. You know, you sort of create 1,000 of these and you page through them. And you know, all of our lives kind of look like this. We have different parts of our life that we inhabit. We are the thing that all those parts of our life have in common. And some of them are bigger, some of them are smaller. People span different things. And so this picture actually became sort of like, you know, it's like these sort of pieces of art that you come back to, and every time you look at it, you see something different. We would sort of stare at this as we talked about things. And we sort of had this point, and I think it was really Johan, my student, who articulated it nicely this way, that rather than think about Facebook as a billion-node network, we could get a lot of mileage out of thinking it instead as a collection of a billion different networks, right? One centered at each different person, right? They're overlapping, right? So the real Facebook network is like this big thing where you take those billion graphs and you paste them together on the points where they overlap, and then you get the whole thing. But one learns a lot by doing this. It also, of course, is useful just from a design point of view, because if you think about the problem that Facebook Newsfeed is looking at, it's how to assemble basically a personalized newspaper for this guy from all the 1,000 or 2,000 pieces of content being produced by all these people. And so the problem that they are thinking about is a billion instances of this, where this is the input, all the stuff being produced here, and this is the audience for it. Okay, so that was the idea. What do I do if I have a collection of a billion graphs? Can I map out that space? Can I talk about sort of what things it has in common and what it doesn't? I should mention there are graphs like this all around, right? So I could take my email, for example, and I could build a similar picture. Here, actually, what's going on? So I don't know which of my friends are actually sending each other emails. So this is everyone who I've sent at least 5 emails to, and then this is when they've been co-recipients on an email from me. I connect them by an edge, right? So if I sent an email that had both of them on the to line, I'll link them, right? And again, we see clusters. My email, as we're discovering, is a lot more homogeneous. This person seems to have a more interesting life than my email life, because this is sort of one big blob. There are definitely clusters. I can actually, I had to work hard. So there are certain people who stand out. We'll talk about that later. If I worked hard, I discovered this was one book that I wrote, and this was the other one. You find little clusters from there. But each of us carries these networks around. And actually, as this suggests, we carry them around in several media, right? So I have a Facebook one. I have an email one. I have a offline life one, obviously, which all of these are projections of in some sense. OK, good. So that's the plan. Think about what we can do with this collection of networks. What's the mapping activity? So one thing we might want to try doing is actually producing some kind of a coordinate system for these things, right? It was definitely sort of revealing that we were able to put all the photos down on this map and look at what they look like. Could we do that with these things? And secondly, what would we compare it to, right? So when we look at this graph, should we say, yes, this is kind of what we expected, or no, this is not what we expected? So in order to ask whether this is what we should have expected to see, we should compare it to some sort of baseline. And one baseline that's always good to start with is something that graph theorists call the GNP model, which was really made famous by Erdős and Renyi in 1960. And the way it works is if someone said, make up a graph, just draw it for me, and it should be sort of a random graph, this is probably the simplest thing you could try. What you would do is you could place n nodes. I placed 6 nodes here, down here. And then for every single pair, you flip a coin with probability p, and if it comes up heads, you connect them. OK, so maybe this is one sample from that. So among all possible pairs among these 6 nodes, I could either connect or not connect them. These are the coins that came up heads, and I got some kind of a graph. And it certainly makes sense if you're going to ask, does our graph look usual or unusual, typical or atypical? We should at least think about the GNP model and what kind of properties it has. So once people began looking at real graphs, which admittedly, Erdős and Renyi did not invent this so as to think about properties of empirical graphs. They wanted to study this mathematical object. There are a whole beautiful theory around GNP, and it relates to a bunch of things in algorithms and combinatorics and elsewhere. But as a model of real graphs, it has some now widely documented deficiencies that have sort of crept in over the past 15 years as we've looked at real graphs. So here are a couple of them. One is more relevant for us than the other. So one is that when people began thinking about this as a model for, say, the web graph, who links to whom on the web, a big problem is that if every node has n-1 potential neighbors, each is the result of a coin flip with probability p, then the number of neighbors you actually end up with is quite close to the expectation. Right? So there's a given average number of neighbors that nodes have, and everyone is quite close to that average. So it produces a relatively uniform number of links around every single node. And that, of course, we don't see on something like the web. Right? On the web, we have pages like Amazon.com, which receives hundreds of millions of inlinks. And we have pages like just an arbitrary random page, which could receive, say, 5 or 10 inlinks. Huge disparities. GNP is not going to do that. Maybe that's a little less of a concern for us, because at least in this talk, we're not really thinking about web graphs. We're thinking about online social networks. And online social networks have kind of a bounded amount of connectivity per person for several reasons. Right? One is just sort of cognitive limits, which is a nice theme that's come up in several talks actually today at this workshop, that there's only so much you're going to be able to devote to linking to people. There's also just a more practical reason, which is actually Facebook caps the number of links you can have at 5,000. But the point is most people don't ever reach 5,000. Very, very few people actually hit the cap at 5,000. Again, there's obviously with social media, there are things, Twitter is not entirely a social network, right? So people can have 1 million followers on Twitter, but that's because it's more of a web-like graph, really, than a social graph in that sense. OK, but there is another deficiency that GNP has, which is going to come into play, which is that real social networks are very rich in triangles. Right? So if I think about, say, this is a proxy for a social network, a group of people, 6 people who may or may not know each other, very often in social networks, triangles close. Right? So like maybe these 2 people, right, they weren't friends, but they became friends. And there are all sorts of reasons why they might become friends. Right? This person introduced them. They had this person in common. All sorts of, right? When you have a friend in common, there's an opportunity for you to meet. There's a person with an incentive to introduce you. One just recurring fact, you see it every time you look at a social network data set, is triangles close, and therefore they're rich in triangles. Right? Maybe this closes. And this actually becomes certainly one of the ingredients of another bit of technology that Laura's introduced to Facebook, which is the friend recommender. Right? If you're trying to recommend people you may know on Facebook, certainly one, though certainly not by no means the only signal there, is to ask, what recommendation would close a lot of triangles? Because that's probably somebody you know and where there might be some incentive for you guys to meet. OK, so GNP does not do that. Right? GNP has no particular preference for triangles. Right? The fact that this person and that person have all these friends in common, there's still a probability of p that that link's going to form. That probability is not modified by the fact there are all these friends in common. GNP is oblivious to triangles. And so that's certainly something that is missing. OK, so GNP is our baseline. And we want to think triangles is one place where we expect some deviation. What else? OK, so I said I want to put some coordinates on the space of graphs. So let me do a bit more math than I've been doing so far. Here's one way to sort of reduce a graph. I mean, part of the problem is this guy's Facebook neighborhood is one of 1 billion neighborhoods. And I could enumerate them all, but there are so many possible graphs on 100 or 200 nodes. Effectively, they can all be distinct from each other. Right? So I'm not going to tabulate how many graphs look like that. There's just one of them. So what I want to do is boil that graph down to a small set of numbers, and then look at how those numbers are distributed in some space. And one thing that has worked very well, and it's been used originally as far as we can tell in the sociology literature, but also in actually computational biology and data mining, in math and computer science, is this idea of taking a big graph and looking at the frequency of small subgraphs. Okay? So here's the idea. I'll say it in words. That's the notation for it. I'm going to take this big graph G, and for pick some small k, like actually just k equals 3 is good enough to think about. Let's look at every set of 3 nodes in this whole graph. So here's a set of 3 nodes. And let's look at the subgraph that they induce. Right? How are these 3 friends connected? They're connected like that. This person is not connected to either of them, but they're connected. Okay? And so what we'd like to know is, over all 3 tuples of nodes, what fraction produce this graph, and what fraction produce triangles, and what fraction produce every other possible graph. Okay? So that's my notation for it. So H maybe is a triangle. G is my big graph. So F sub G of H would be the fraction of 3 node sets that induce a triangle. Okay? So for example, with 3 node graphs, this gives me a signature for this graph, because there are 4 possible graphs on 3 nodes. Here they are. the graph with no edges, the graph with one edge, this wedge shape, and the triangle. And maybe 18% of all 3-node sets create the empty graph, and 37% produce this, and 14% produce that, and so forth. Okay, and that gives me this short little vector that's at least a compact way of describing this graph. Obviously, it destroys a lot of information. But that was sort of my point, right? This graph was somehow too expressive for me, and I wanted to reduce it down to this very compact point. I could do it at higher dimensions, right? I could do, say, all 4-node graphs. I could say, what's the frequency of this or this or this? And there are 11 graphs on 4 nodes. Not a fact I expect any of you to know. And each of them has some frequency in this big graph. OK, but we'll think about 3-node graphs right now. So this is actually a 3-dimensional vector, actually, because it's 4 numbers that add up to 1. So there's sort of 1 degree of freedom here that's not useful. And so I could actually draw it for you, right? I could take, we didn't take all billion for this because that's computationally expensive, and after a while you start to get the idea, actually. It sort of fills out, this part of the space is going to fill out. So we took a large sample of network neighborhoods, all of the same size, actually, so that size effects wouldn't come into play, although it sort of looked the same basically at each size. And I can draw it for you in the sense that I'll take a big cube, and I'll have 3 of these things be the axes, and then there'll be, the 4th one will be implicit, because the 4 numbers add up to 1. OK, so everyone see what I'm trying to do here? Reduce down to coordinates, and then draw it. So that would look like this. So my axes are the frequency of the empty graph, frequency of the triangle, and the frequency of the one-edge graph. And so the missing one is the wedge. And the wedge is actually sort of an interesting one, of course, because it's the thing that wants to close, right? In a social network, that is what wants to form a triangle. OK, and I'm going to draw this. And so just to orient, right, so way up here are graphs with almost no edges. Way over here are graphs with almost no edges. Way over here are graphs that are completely dense with triangles. Toward all 0 is graphs that have many, many wedges, because the missing mass is wedges. OK, and so now we're just going to take, every graph becomes a point. And just like with the photos on the blank canvas, here's my blank canvas. We put down all the graphs, and we get a shape. And that actually is the space of all the Facebook network neighborhoods laid out in this space. And it's sort of it's an interesting shape, right? It's sort of, now it's, we're in 3D here, and unfortunately I didn't draw for you a kind of revolving cube display of it, which would be cool, but I didn't do that. But I can tell you that it goes up and down, as you can see, and it actually is slightly serpentine. It sort of twists toward the back as it goes. OK. So what is that thing? So before we kind of start free associating too much, we should remember, what were the heuristics we had from the photos, right? We should look for where the density is. Well, we see that. We should look for coastlines. We should look for where the points don't sit. And we see there are a bunch of those. There's a bunch of empty space here. And we should ask, again, when there's empty space, is it because people can't live there, or they just don't live there? And that actually turns out to be quite interesting here, because there are 2 constraints operating on this cube. The first constraint is actually simply graph theoretic. Okay? And so, for example, here's an interesting fact in graph theory, which is sort of fun to try proving. It's a bit challenging, but not hopelessly hard. That you cannot build a graph where the frequency of this is greater than 3/4. Okay? As in, if I told you build a graph where every single 3-node set is this, you actually couldn't do that. You would try, and you would discover that certain of your 3-node sets were actually just the empty graph. And in fact, if you tried, not only would all of them not be, but in fact, the best fraction you could get in the limit, for large graphs, is going to be 3/4. So that means the upper 1/4 of this cube is empty for purely mathematical reasons. We are not observing here a fact about people. We're observing a fact about graphs. Similarly, the wedge, which is just the complement of this thing, also can't occur more than 3/4. And so a certain region here is empty. But actually, if we look down here, much more of this space is empty than it has to be. There are a bunch of graphs that could form there, and they just don't. So up here, people can't live here. But down here, people just don't live here. Right? So down here would be a graph with a ton of wedges. And those graphs just tend not to happen, because wedges are the thing in social networks that want to close. And so people just don't form social neighborhoods that have tons of open wedges in them, because those wedges just kind of decay, and they go away, and we just don't see them. OK? So there's sort of an interesting thing here, which I think comes up a lot when we start looking at this kind of network data, that there are sort of these 2 constraints operating, properties of graphs and properties of people. And we're really seeing them intersected when we try looking at a picture like this. There are a bunch of interesting questions here about, what is the space that graphs could actually fill out here, right? So people, that's kind of a messy thing, but at least we could maybe ask the question, what is the actual outer limits of where graphs could sit? That's a hard problem, right? It's a problem that there's actually a very active area of work, the theory of graph homomorphisms, that's producing a lot of nice results on. And even just doing this for 3-node graphs would imply some hard results in combinatorics. For example, a very nice result of Rezborov from 6 years ago. OK, there's actually one more question that we were supposed to ask here, which was when you see a one-dimensional thread, you should ask, what is the river or the mountain range or the interstate highway that flows through it? Remember that? And this is all 50-node graphs. But as you go up to 100-node, 200-node, this sort of tightens up down to something that's quite thin. Right? This is sort of thin tube snaking through the space. And the river that it's near is actually GNP. So what do I mean by GNP? So n here is not important. But if I think about GNP, the set of all points that GNP could occupy here is parameterized by p. P is my free variable. I could set p to 0, I could set it to 1, I could set it anywhere in between. And when I set p to 0, well, I know what that graph is. That's a graph with no edges. And that point is here. When I set p to 1, that's the graph where every edge is present. Right? They all must be there. And that graph is here. It's all triangles. And as I range p from 0 to 1, it fills out this curve. Right? So for a given value of p, right, the frequency of triangles is going to be, well, the triangle has to form, so it's p times p times p, p cubed. And the wedges, well, let's see, p times 1 minus p, and there are 3 ways to do that, so it's a formula 3p squared 1 minus p. And we could work that out. The point is it's this parametric curve in space, and it's cubic. Right? And so it actually has this serpentine shape where it goes up and down, and it's also sort of curving toward the back, because that's what parametric cubic curves are able to do. So, and it actually runs quite well through this point. So at least at this level, we're actually learning a fair amount about how GNP conforms to this. Now, people didn't settle equally along all banks of this river that GNP forms. Right? They're off to one side. And that one side is actually the direction that you would expect, which is social networks are overly rich in triangles. Right? So here are triangles, and people are here, but they're not there. Okay? So things are shifted. And they're shifted in the direction we would have expected, which is toward more triangles. OK. So that's sort of one way of thinking about these points, about the space of all graphs. A couple more thoughts I had on this, which I'll jump over to get to a question that we looked at with these network neighborhoods, okay, and a measure that turned out to be kind of useful in this process. So let's go back to what we were thinking about with these network neighborhoods, which was the network neighborhood is the input to newsfeed, right? This is the set of friends you have. This is how they're connected. They're producing content that's coming at you like a fire hose. We want to figure out what to show you, how to filter things. And if we want to do that, so here's V. I drew a smaller cartoon picture now. V is the person. And these are all their friends. And we see, they have some clusters and some other things here. And I want to know how to prioritize content. If I want to know how to prioritize content to people, it's very useful to know which are their strongest social ties, right? Who are the people they have the closest relationship with, and who are the people they have more distant relationships with? Because sort of the working heuristic here for thinking about prioritizing content is that there are the people who you have very close friendships with. And there you want to hear what they had for breakfast, and that they went to the pool today, and all sorts of stuff. And then there are the people who you have very distant connections to, right? You're friends with them on Facebook, but they're what sociologists call a weak tie. And you do want to know when they change jobs, they get engaged, they have a baby. Right, so you want to see the major life events, but you don't necessarily want to see everything that happens every single day. And it's these sort of concentric circles around you that Facebook would like to estimate. But Facebook isn't there sitting alongside you really knowing everything about your whole life. It has the data that it has. So the question is, again, back to the kind of Martian off to the side observing the data with lots of computing power, what could we actually learn about who the strong social ties are just from this network data? Right? How far can we get along that road? OK, so that's a question that we wanted to ask with these network neighborhoods. Right? We have a sense of what they look like. We have a sense that triangles are key. Can we look at this algorithmic problem of finding strong social connections? So triangles, again, are going to play an important role. And they've really played an important role for a long time in the theory of social networks. And the idea is to think about this parameter, which I'll call the embeddedness of an edge. Okay? So I think about, say, V, and I think about the edge that V has to one of these nodes, just this link here. And I'll say the embeddedness is the number of triangles that contain that edge, or equivalently, the number of mutual friends. Right? So let's think about here. This is a good example. So V and W are a link, and they have 4 mutual friends. Each of these is a friend of both of them, so they're part of 4 triangles. Okay, so that relationship is embedded in 4 triangles. And what the theory of strong and weak ties from sociology tells us is that if an edge is highly embedded, it's likely to be a stronger tie, a closer friendship, right? More affective strength there. If it's less embedded, it's a more distant friendship. Right? So the people that you know really, really well, we should expect you have many mutual friends in common for all sorts of reasons. You travel in similar social circles. You've acquired these mutual friends. The two of you have an incentive to sort of know the same people. Lots and lots of reasons for that. Whereas someone that you don't know very well, they're in a different cluster of your social life. You may have very few mutual friends in common. Right? You have your social world. They have theirs. You do know each other, but there's just much less there. So if we wanted to find who your strongest ties are, the sort of baseline you would have to try first is let's just take your friends and sort them by embeddedness. Right? Take all of them and just rank. Right? The person with whom you have 50, 60 mutual friends, that clearly is significant. Right? And the person with whom you have 2 or 3, maybe they're a more distant tie. And how does that do? Like, what does that actually find? So the funny thing is, and there's a case where you have this intuition, it's really compelling, and it's correct. Right? Triangles do indicate something about tie strength. But once you actually go to look at what's happening on Facebook, you realize you need to do something extra. Because let's actually try it on this guy from Facebook and all his friends. You remember this graph. Suppose I actually rank this by embeddedness. Well, what's it going to find? It's going to find all of these nodes. Because these are all his coworkers. And the coworkers are all heavily there. Right? They're all on Facebook, and they all friend each other for all sorts of reasons. Right? You just sort of at work, they send each other friend requests. They actually need to be in the same kind of work groups to exchange information. So there's just a lot of linking around here. So any random coworker here, you go, how many mutual friends are there? And there's 20, 30. There's a lot of mutual friends. But some of these people you don't actually know very well. It's just you're in the same social group, and you just acquire these common friends by just brute force, basically. Similarly, in this alumni group, back in college, you friended all these people. And so again, it's a group. It's very large. And so there's going to be a lot of these links. OK. So there's almost like a currency conversion problem. A mutual friend here somehow just comes in at a lower rate than a mutual friend here, right? Here is somehow your family is somewhere here, but there's just fewer of your family. Still a strong tie, but there just aren't enough of them to produce all these mutual friends, right? So it's sort of like, a mutual friend here is worth $1 to the sort of nickel or dime that sort of each mutual friend is here. How do we do that? Like, there's a problem there. OK. And so here we again went back. It was an interesting sort of challenge. We went back, and as I said, this picture sort of worked for us like this sort of work of art you keep coming back to, and every time it tells you something new. And we had been sort of obsessed by this and this. We're like, oh, the graph, it's clusterable. It has these beautiful clusters in it. But there were other things. And what began to jump out at us, so much that now when I look at this picture, it's sort of all I see, is this point down here. I don't know how many of you sort of noticed that point when I put it up right away. And probably it did jump out at you. But that point at 7 o'clock, because it sort of sits there and it has links out to just all these different places, right? That point is also somehow special in its own way. What is that point? That's actually his wife, as it turns out. Okay. She's neither a coworker nor someone he knew in college. But she sure does link to people from a whole bunch of different social groups at this point. Right? And you see it. When you draw the graph and you spring embed it, you certainly see that point. And if we see it, then our sort of Martian algorithm friends with much more computing power than we have, they should be able to see it also. But what did we use to see it, right? That's the question. So we hit upon, so Lars and I were thinking about this, and we hit upon this question, right? It's sort of in the nature of algorithm design that when you are trying to sort of invent a better algorithm for something, you try to find the hard case that your techniques currently don't handle. And we felt like with this we had hit upon the hard case. Right? And here was the hard case. Given a Facebook user in a relationship, can you find their relationship partner from just the network structure? Right? That's how we arrived at that question. Right? So the point is, it's actually a very, very precise question. The input is this. I have the ground truth because the person declared a relationship partner in their profile. And you're allowed to make one guess. And you have to guess the right way. And OK, so we should certainly see how embeddedness does for this. But we should see how other methods do. Right? Maybe there's a better method. And this is sort of forcing us to try to look for a better method. I should mention there's a whole bunch of things around here that a bunch of footnotes to this, which I won't have time to get into. There's a big issue about, is this really their relationship partner? Right? So we know that girls on Facebook in the age range 13 to 17 often declare their best friend as their spouse. And so we steered around that landmine. And there are some other things you have to be careful with. But fundamentally, there were some sanity checks that we did, which I won't have time to get into, that suggest that for the set of people that we were looking at, which was based on a large random sample, I'll get back to, of people of a sufficient age, we were actually, it appeared that these were basically actually the relationship partners. OK. But it is certainly one thing that runs through all of this, right? And you should be watching all of this through this lens is we're only able to look at the things where we have data, right? Yes, we have 1 billion users and we have all these people, but in the end, we're studying people who were active enough on Facebook that they did declare their relationship partner on Facebook, right? And that's what we're studying. And we're not studying everybody in their relationship partner. OK, but that was the question. So here was the idea that we had, right? So what is, I mean, let's just ask the question, right? What's different about this person than all those people? Well, these people's friends all seem to come from the same cluster, right? Yeah, you had 20 mutual friends, but if we somehow understood that was a cluster, those 20 mutual friends were all from that cluster. This person, with their 20 mutual friends, they're from all over. All over somehow seems significant, seems important somehow. So maybe instead of just counting the mutual friends, we should look at the structure on those mutual friends. So here's an idea. So here's VW with 4 mutual friends. Here's VW with 4 mutual friends. Here, the mutual friends are all connected to each other. And here, they're actually sort of disconnected, right? There's only one link among the 4 mutual friends. Right? They're dispersed around. So right, if they're well connected, that suggests something about the relationship, if the mutual friends. And if they're not well connected, that also suggests something. In particular, if they're well connected, it suggests that maybe these mutual friends can all be explained by one social focus you have. And if they're not, you really need several foci to explain them, right? This is right, so when they're spread out, this is a relationship that defies easy classification, such as we want these significant relationships to do. OK, and so in that sense, what's sort of intriguing here is it's a kind of what sociologists call a bridging or brokerage role. But it's being played jointly by V and W together, right? So often we talk about people in a social network as being a broker, that they bring together disparate groups. They sit at the intersection of disparate groups. Here, right, neither one of these people is on their own a broker because there's the other one. But the two of them together are acting as a broker. If you sort of contract them to a point, now they're playing a brokerage role. And the funny thing is that the sort of brokerage they're doing is supposed to be implying a form of tie strength. This is somehow a special relationship because they're all dispersed. All right. Let me do 2 slides of math to sort of talk about how we actually implemented this, right? So what do we actually mean by dispersion? What do we mean by not well connected? We tried a bunch of things. And sort of one that actually worked well and was actually not very complicated to compute is the following. So here's that same graph embedded in the big graph. So here's VW. Here's their 4 mutual friends. Let's say CVW is the common neighbors. And let's simply look at if we were to delete these 2 people, and this is sort of how sociologists often think about bridging. Delete these 2 people and ask how far apart are their mutual friends after that deletion. Right? Currently, if their mutual friends had to get to each other through a short sequence of hops, they could all get between each other in 2 hops, by definition, because they have V and W in common. But if I took out V and W, who knows how long the next shortest path might be. It might be a long way around. And the longer it is, the more significant that is in its bridging role. So that's what we're going to look at. We're going to say it's the sum of the distances among all pairs of common friends after deleting these 2. Or in other words, the sum of all people in the set of their distance in the graph with those 2 deleted. All right. I have to play with this definition a bit. But I'll call that the dispersion of the edge. It's how much it disperses its common endpoints with respect to this distance function d. I also need to figure out what this distance function should be. Right? If the distance function is counting hops, there's a little pathology to that, because if I take away V and W and now 2 nodes can't reach each other at all, what's their distance? If it's infinite, that doesn't tend to work well when you put it into a sum. Otherwise, I need to. So OK, so we played around with things. One is actually a very simple one. I could just say their distance is 0 if they're actually directly connected and 1 otherwise. Or I could generalize that to say their distance is 0 if the shortest path between them has at most k edges for some k, and it's 1 otherwise. Right, so I could just threshold it. I could say your distance is actually just 0, 1, near or far. Near means at most k hops to get to the person. Far means more than k hops. And I'll just have these near-far distance functions. We also discovered that when we just did this, so we're closing in on what we did. We're going to do this with a particular value of k. One problem with this was it wasn't strong enough to avoid the coworker problem, which is when we add up all the pairs, the problem is these people just had so many pairs that even though the distances were small, you add them up, and these people still somehow rank too high. So we somehow should take into account that it's more impressive when you get a large sum without having very many mutual friends. So we should normalize it. Dispersion divided by the number of mutual friends you have, raised to some power. OK, so I now have 2 knobs I can turn on this thing. The first knob is what k should be. That's an integer, so it's going to be like 1 or 2 or 3. And I have a second knob, which is a real number, which is the exponent on this. OK. And it turns out when you search over this, k matters a fair amount. Alpha, things are sort of relatively flat. Something which is nearly optimal and sort of makes intuitive sense, k equals 2 and alpha equals 1. So alpha equals 1 just means you're dividing by the number of mutual friends you have. K equals 2 means you're near if it takes at most two hops to get between people, and you're far otherwise. So the icon is the following. That what I'm doing is saying take VW and look at pairs of mutual friends, S and T, and look at count how many pairs don't have a third mutual friend in common. Because that says they're far. There's not a two-step path between them. And that became sort of the little 5-node subgraph that we felt was actually somehow capturing this notion of a strong relationship. The two of you, two mutual friends you have, and no third person who acts as a shortcut like you do. Okay? And you can think about that, pick some sort of strong tie in your own life. Think about two mutual friends you have and how you may be the only two people that those two people have in common. Right? OK, so that's what we were looking for. A little 5-node subgraph where one of the, quote, nodes is actually a missing node. All right. So that's now something you can go and you can run on Facebook data, and you can ask, how well is this actually doing? All right. So here's what we did. And again, this was sort of chosen after a whole bunch of thinking about, about the problem and trying out a bunch of heuristics also. So we're going to evaluate how this does at, remember, our challenge problem. I'm going to give you a network neighborhood. I'm going to withhold the answer, who's the relationship partner. I'm going to allow you one guess, and we'll see how you do. So people who declare a relationship partner in their profile, which, according to the way Facebook works, is a symmetric thing. You can't declare you're in a relationship with someone unless they also link back. We selected, basically, uniformly at random, subject to these 3 conditions. They had between 50 and 2,000 friends. Remember, Facebook caps you at 5,000, but we were sort of cutting out a couple of % of people who go beyond that. Below 50, there was the issue of whether you were sufficiently engaged with Facebook to even make this a sensible activity. And you're at least 20 years old. OK. And for each user, we're going to now rank their friends by a bunch of metrics and see how we do on this problem. So one is the embeddedness. How many mutual friends you have. And again, that's our baseline. Because the point with embeddedness and tie strength is you go back into the sociology literature, and those two concepts really, in a sense, almost had never been disentangled. Right? Embeddedness was so much the proxy for close relationship, strong tie, that often the two were never really distinguished. We're trying to put some distance between them. We're trying to say that's one way to measure it. We'll also use dispersion, as computed in the last one. And then we'll also ask a set of other questions. We'll say, this is asking the structural question. The input is a graph. I want you to find the relationship partner. But to be fair, Facebook has access to lots of other signals about you. And if those were way better at doing this than the graph structure, we should know that. Because maybe the whole point of using graph structure is lost. Right? So what are some other things Facebook knows about you? Right? It knows how much you message this person, how much you like their content, comment on their content, how much you view their profile, how much you're tagged in photos with them, how much you've checked into places with them, how much you've been at events with them, a whole bunch of things you could use. And you run through all this and you ask which of these features turns out to be most informative. And actually the two that were most useful, and again, I'm sort of jumping ahead to some of the punchlines so as to prune the information here, but I'll tell you that these two are the most worth comparing against because the other ones do worse. The number of photos you're both tagged in. Very good sign of, is this a close relationship, right? You both stood in front of a camera, click, someone tagged you. Also, the number of times V viewed W's profile. Turned out to be more informative than messaging, commenting, or liking profile viewing. OK. And so we'll also compare, if we rank by this or that, how do we do? All right. And this is the question. For what fraction of all users in our sample is the top ranked person the actual relationship partner? And remember, everyone has at least 50 friends. So blind guessing has a 2% success rate. Okay. All right. So here goes. I'll walk you through a table here that shows some results of how we did. So the first two numbers are, what kind of ballpark are we in? And the first thing we see is that dispersion actually does more than twice as well as embeddedness at this task. Right? 50% versus 25%. And the other is just how often it's correct. Right? So I should say, we got to this point, and you run the experiment, and you see how you're going to do. And I was prepared to be happy if, say, it was right 10% of the time. And why was I prepared to be happy? Because, guessing is 2%. So you're getting a 5-fold lift, right? 20% correct is an order of magnitude lift over guessing. And we're getting 50%, right? More than half the time, we're actually, with one guess, getting the relationship partner. Right? It jumps out from the network structure. And much more so than if you're just using embeddedness. OK, how about activity-based metrics? So dispersion is actually better than any of the best of the activity-based metrics. Right? So if I have all the photos that you appeared in with everybody, that still is not as good as if I have the graph structure, and I can compute this metric. Or if I have all of your viewing activity, not as good as I have the graph structure. And again, it was crucial that we actually used dispersion and didn't use embeddedness. Right? If we'd sort of stuck with embeddedness equals strength of tie, we would never have seen this because these activity-based metrics would actually be beating it. Right? And it would appear incorrectly that activity was somehow a more powerful thing. But that's actually not true if you have the right network measure. We can break this down further, right? So some people are married, some are just in a relationship. It's easier to find the partner if they're married than if they're in a relationship. Makes sense. There's sort of presumably more network context there. Structure certainly does well for married. Relationship actually, now activity-based metrics start to do well, start to do better. So if the person is in a relationship, right, so all is an average of these two things. There are about 400,000 of these and 750,000 of those in our sample, which is the relative rates of them on Facebook. And what you're seeing is actually the winner for relationship is actually profile viewing. People in a relationship do a whole lot of profile viewing. OK. Photo and dispersion is actually very, very similar. OK. There's a gender difference, which is interesting. Actually, let me quiz. All right. Chance for a quiz here. I'll pull it back. OK. You can think to yourself, I won't take a vote, but you can think to yourself, is it easier to find the relationship partner of a female user or a male user? I guess we could do a quick. OK, how many people think it's easier to find for female users? How many people think it's easier to find for male users? All right, that's a split. The answer is it's actually much easier to find for male users. Which has actually surprised us. I think we would have guessed the other way. Why is it easier? Well, of course, it's an interesting question, right? I mean, I'll phrase it as a question more than as a. It certainly is true. I mean, what it's saying. Actually, I'll say something which sort of resolves the mystery a bit later on. But what it's certainly saying is that men have this sort of single person in their network neighborhood who is playing this role, and it's their spouse. Women have more than one person who's playing that role, right? And that's what's happening. Right? As I'll show in a couple lines, that person is often a family member. Family members actually make up the gender gap. If you look at sort of relationship partner or family member, then the two genders are almost equal. OK. It's also interesting. So relationship is, we actually looked at users who said they were engaged. And somewhat reassuringly, engaged interpolated exactly between relationship and married in pretty much all the dimensions. If we actually combine all the features by machine learning, embeddedness, dispersion, photo profile, and also commenting, liking, events, messaging, the whole thing, then actually relationship and married, you get very similar accuracy. You get about 70% in both cases. Right? So somehow, it's like there are complementary strengths, right? Structure is better for married, activity is better for relationships. They sort of all balance out. And roughly 30% of the time when dispersion is wrong, the guess that makes is actually a family member. Right? So about a third of the incorrectness is explained by guessing family members. The other 2/3, who knows, right? One still has to diagnose exactly what's going on there. And actually, this is gender disproportionate. When it's wrong, it's much more often wrong on family members for female users than for male users, and that's where it makes up the gender gap. OK. Let me show you a couple other things we found, because essentially once you have this lens on things, you begin to sort of wonder, what else is going on here? So you have a sense that like the network thing is working because as you have this relationship, gradually the network forms around this relationship and produces the signature that we're seeing. And if that was true, you should expect to see that we're getting better and better as the relationship goes on. And that's also true. So here is how we're doing on married users in the time since the relationship was reported, 0 to 24 months. Now, I should say time since reported is not equal time since they got married. For example, two people who are 40 and have been married for 10 years, they just joined Facebook, they declare they're married. All Facebook can see is that's time 0. So it averages in a bunch of other stuff like that. But we still see that the network measures are all getting better and better. The photo measure is getting better. Profile viewing is getting worse, actually. Right at time 0, lots of profile viewing, then less profile viewing. But the network still sort of fills in around people. That actually is even more extreme in the case of the relationship. Here's profile viewing. It's like way high. It comes down. It comes down a lot, right? And actually, the two things cross, right? So at 12 months out, structure is now a better predictor than profile viewing. One thing that we still find a little mysterious I mean, it's just sort of one minor point here, but it's sort of baffling that the power of photo co-tagging and the power of dispersion in finding relationship partners is almost identical sort of month by month. They go up just together in lockstep. Don't fully get why that is, because it's not that the two are somehow disguised versions of each other. It's not like, oh, really one's the same as the other. As we see here, they're not the same. Somehow here they are the same. Something we don't fully get. Let me just run through one more thing, and then I'll wrap up with some closing thoughts on all this. People asked us, and so we went and looked, like, can this help predict breakups, right? I mean, you want to sort of. So, and there's I don't know. I mean, it's not clear, but here's just one suggestive thing. It sort of bundles together a whole bunch of stuff that, maybe should be left unbundled, but I'll mention anyway. We simply asked the question, take the cases where dispersion was right and the cases where it was wrong. Control for a bunch of simple things like the time since the relationship was reported, which clearly affects it, and the age of the users, which also affects it, and gender and things like that. OK, so control for a couple things. And ask, take the case where it's right and where it's wrong. It turns out that on the cases where it's wrong, there's a 50% higher chance that the user will declare themselves to be single 2 months out. Okay. Right, so we take the data, we go 2 months out, and we look at who transitioned to single, which again, most relationships don't break up in 2 months, and so we're talking about a kind of 4 to 6% rate here. I mean, so we're not talking about high probabilities. But there's a 50% increased rate of breaking up when the algorithm was wrong. Right? So it somehow says when the algorithm was wrong, right, when dispersion didn't detect this partnership, there was something, I don't know, less robust here, at least as this is suggesting. OK, again, as I said, this is not breakup prediction. This is simply something suggestive that does pack together a bunch of things. Right? We've taken out the time since relationship reported, a couple other things. But OK, so I want to just end with a couple of conclusions. Right? So we've looked at sort of the space of all neighborhoods. Right? Facebook is this collection of everybody with their network neighborhoods. We've tried to sort of delve in and do a particular thing with it. Namely, can we find these particularly significant people if we had the right network metric? I want to talk about a couple other reflections. The first one is actually mathematical in a sense, which is sort of a question more than a result. It sort of was intriguing to me. Lotzi Lovas, who's a famous Hungarian mathematician and very, very influential in both math and the computer science community, gave a bunch of talks about 10 years ago where he made this point that if you look at graph theory as a pure subject, study of graphs, there are a number of theorems in graph theory that basically say graphs of a certain type have sort of descriptions of constant size in a certain sense. So one famous one is the Semiretti regularity lemma that says that dense graphs can be sort of described as sort of a constant number of pieces glued together in a kind of random-like fashion. There's also the Robertson-Seymour graph minor theorem, which said that graphs that sort of have a forbidden topological structure basically look like graphs that can't be embedded on a surface plus a constant amount of sort of extra stuff that doesn't fit. So actually, both these theorems, and these are both sort of theorems in pure graph theory, have this property that says graphs in this family equal constant size description plus constant amount of extra unclassifiable stuff, which of course would just go into the constant size description. And the funny thing was, like, I had that intuition just from thinking about graphs, and it sort of kept popping up as we worked on these network neighborhoods. So what Lotzi's question had been 10 years ago is there a kind of informal structure theorem for real social networks that you can sort of give a kind of constant size description of it? And I always had that in the back of my mind, along there with the Martian scientists and everything else, as I was working on this. And it did feel like, as we were looking at this, that one way to think about people's people's neighborhoods, right? So your user V, is that your neighborhood looks like a constant number of clusters that sort of look like GNP. Each of them is their own mini GNP. These are your coworkers, your friends from college, friends from whatever grad school, family is here, right? It's sort of like a flower with petals sticking up. And then sort of plus a constant number of nodes that defy easy classification, right? Your sibling, your relationship partner, right? People who reach out into many of these things. Right? And they reach in for different reasons, right? This is sort of the whole point, that we found the relationship partner because they had all these links out. There were also family members there. And in the case of your spouse and your sibling, or your boyfriend, girlfriend, and your sibling, look this way for different reasons, right? Your sibling actually grew up with you through all those life stages and has those links because they encountered them as you did. Whereas your relationship partner typically is someone who acts almost like a time traveler in your social network, someone who you systematically reintroduced into all those social groups after you met them. But the effect when we look at it now is sort of similar, right? This constant number of nodes that defy easy classification. And so I think there's sort of an interesting question about, it's not hard to think about, can we create a generative model of graphs like this? constant number of big homogeneous clusters plus constant number of extra nodes? And then can we talk about sort of ways of identifying that structure when we go look at data? OK. Let me just wrap up with a few final open questions, and then I will happy to take questions. So this has been sort of one take on what are some things that you can get in network neighborhoods. There are a lot of other nice kinds of things. I mean, I think even from thinking about talks today, this nice work that Tina Eliassi-Rod has been doing on roles in networks, I think there's sort of a nice question here about this was a kind of role. Are there other sort of structural signatures for other subtle roles that are going on in here? Relation of network structure to the spread of information, right? If you have a sort of open or closed neighborhood, that can affect how information flows, another thing we've heard about in the workshop today. And of course, one thing that we've been thinking about, the implications of systems designed to share information, like Facebook newsfeed. And again, sort of also a warning, right? And the warning is, with all these things, we're seeing what's in the data, right? We did this thing with relationship partners, but we could only see what was there. And here I'm actually reminded of about 8 years ago when I was working on query logs, search engine query logs. I got this unsolicited piece of mail from an AOL user who read an article about how I was looking at query logs and said, the thought of anyone compiling a profile based on my online searches delighted me. I'm a senior citizen, live in senior housing. I'm one of 2 people in the building who own and know how to use a computer for research. For this reason, I'm kept busy researching topics for other residents. My grandchildren all come and visit me at various times using my computer. 8-year-old goes to K sites, teams to their sites, and the college student has been known to download rap music. If one looked at my search history, they would conclude I have multiple diseases and medical conditions, have interests that span the trail of human knowledge. I go on, but I believe you get the gist of what I say. I hope if my data is in your cache mail, it does not screw up your research too much. And the point is, that this is the thing you wrestle with, right? That you can only see what's in the data. The newsfeed algorithm can only see what's in the data, right? This is sort of this is the lack of domain knowledge that sort of confounds all these things. I should mention there are all sorts of interesting research questions in there that if you actually had a sort of mixture model of activity, maybe you could actually separate them a little bit. But anyway, OK. So, but not to rebut the main point, which is completely true. So I think that's the one I think we have to remember, that we can only see what's there. So just to wrap up with one last set of reflections, the point really is that even with all their limitations, what this data is giving us is a glimpse of something that social networks have been with us ever since humans lived in social groups. And yet it's really sort of this new perspective on them, right? This different way of looking at them. Right? It's not necessarily a better way. It's simply different. And different always leads to sort of new questions and the chance to merge things with existing lines of research, with the kind of subtle, nuanced questions that have been asked in the social sciences for a long time. And so the question of what's the right framework for capturing the structures and phenomena we see, very, very interesting and hard question. And something I should also put on the slide, because it's sort of, one can't talk about this topic without at least putting that question on the agenda, that we should also, at the same time, think about what are the dangers when we go to stockpile this much personal data about people in one place. And one has to be careful. One has to think about privacy as a research issue in itself. And I think the point is that in this big mapping activity we've been doing, the language for building the maps has been fundamentally mathematical. Right? It's been computational and mathematical. And I think there's really an opportunity here for fundamental mathematical models to really inform the kinds of questions that we're going to ask as we proceed along this whole line of research. Thanks very much.